All right, let's talk about functions. Before we get started, anyone have any open questions, comments, anything? What? Oh, yeah, Pat. We can talk after class. I mean, yeah. Any questions not about my sermon? If you weren't a TA, I'd give you a better answer. But all right, let's talk about functions. A topic you learned quite a while ago, but of course we're talking about functional programming. Let's dive into this a little bit more, and specifically functions that we can use with data structures. I showed this a little bit in the last lecture. We had some code that used some of these kind of foreign-looking methods. Let's talk about what those were and dive a little bit deeper into each one of them. Mostly just show rapid-fire examples of the types of functions that we can use that make our syntax a bit more expressive. With functional programming, you'll find that instead of describing what our code does and how instead of explaining how our code does what it does, for example, the accumulator pattern that we did in 115, it was, okay, initialize this variable to some initial value. Now iterate over these values and sum up all of this information into this accumulator, and then return that accumulator. We're very much so describing how our code does what it does. With these with a more functional programming mindset and approach and way of thinking, we're explaining what our code does in our code. Instead of saying, okay, let's accumulate all this stuff in this variable and then return that variable after we've accumulated everything. With functional programming, we're going to say, in that specific example, take this data and reduce it using this function into this one value. It's going to be much more expressive, as I think you'll agree. All right, so for our lecture question, write a method, this average in range, and I remember cut and pasting. I recommend cut and pasting these. This is a capital I, average in range camel case. That takes a list of doubles and returns a function that takes two doubles and returns a double. So we got a couple of moving pieces here. So we have a method that takes a list of doubles and returns a function. Something we haven't seen yet is returning a function. So we're going to return a function, and that function is going to compute the average value of all the values in the original list that are between the two input values. So we want to find the average of the values in this list based on the average of the values in this list that are between these two doubles, where the first argument, or the first parameter is the min value, and the second parameter is the max value, excluding the endpoints, though I'm not testing you at the endpoints, so just don't test at the endpoints, you'll be fine with that, but excluding the endpoints. The reason I say it like that is because being doubles, the endpoints really might not ever actually get hit if we have some truncation errors. So the endpoints, when we're talking about doubles, can get a little spotty. So I'll say excluding the endpoints, but we really shouldn't be testing at the endpoints with doubles because equality with doubles, as we know, is not reliable. If they were ints, we'd have more well-defined behavior here. And finally, a test suite to be able to test this functionality. And mostly with that, I want you to get used to the idea of calling a method that returns a function and then testing that function for the behavior that you expect. This is something you'll be doing with the homework assignments. So I want to make sure you have some hands-on practice before you dive into the big assignments. Both of the assignments, I provide a decent amount of code, especially genetic algorithm. I provide you quite a few methods that return functions. So the testing in this specifically, if you're doing gen algo, will get you ready for that. To call my methods, get those functions that are returned, and use those functions appropriately. Use them for their intended purpose. Is this you, Nick? on Twitch? Is it? All right, well, another TA, I can't answer it then. No, I've had the Pro for a while. I've been using it every lecture this semester. That's why I watch chat on the Pro, and then I use my Mac for the slides. That's how I can watch the slide. Can I get a pug in the chat? You can. Yes, you can, apparently. All right. All right, let's talk about sorting one last time, at least for 116. Maybe it'll come up. It might come up again, but probably the last time in lecture that I'll really talk about sorting is, and I wanted to use this as an example of returning a function. So we saw that we can sort based on any comparator that we want, but there was something a little hidden there, a little subtlety about that that is limiting. If we're talking about functions, we can't take advantage of state, or rather, at least we shouldn't take advantage of state when we're talking about functions. Actually, no, I'll say we can't, because I don't know. We could have global state, but I'll go back to we shouldn't. We shouldn't have any state that we're using in our functions, or else that defeats the purpose of a function. To an extent, at least, they're not what we call pure functions that have this very well-defined input-output behavior. If they're relying on any sort of external state, then they're not pure functions. So what if we want to sort our elements based on some value that we don't have until runtime? So for example, if I have a set of points, and I want to sort them based on their distance to a reference point, how do I do that if I have a pure function that I've already written? How do I actually get that done? So, and the way we're going to do this is have a function or a method that can return a function with that kind of state built into it, completely baked into the function that we're returning. So we still have a pure function, but we're going to create that function at runtime based on some input that we're given. So if we want to sort points based on some comparison point, we can write a method that's going to take that reference point and return a function that compares two physics vectors based on their distance to that reference point, our basic comparator. It's going to take those two physics vectors, compute the distance, each one of them from the reference point, and use the less than operator to sort in increasing order. So this is a pure method. It doesn't depend on any state, and it returns a pure function. So we're in the world of functional programming, but we still get the flexibility that we would have had if we were taking advantage of state. If we had this reference point stored in a state variable and had our comparator as a method depending on that state, we can get that same functionality, but we're going to create this pure function at runtime based on whatever point we're given. So we can still avoid any type of state, meaning we still get the advantage of being completely parallel, completely independent. We can distribute this to a massive scale. We still have those advantages, but we still have the flexibility that we had when we had state. We're just going to bake the state into a function, so we have a pure function that did depend on some idea of state, something that can change, something that we don't know what it is until we have it, until we need this thing, and then return that function. So, and the syntax is the same as returning any other type. That type for our function, in this case, a function that takes two physics vectors and returns a Boolean, we're going to have that as the return type of our method. So for the lecture question, you're returning a function that takes two doubles and returns a double. Well, that's your return type. Your return type is that function, and we have this idea of returning a function with some information already baked into it. So notice I'm using reference point inside this function that I'm returning. And now if we want to sort based on this new comparator, we're going to create a new function. We're going to call distance comparator that takes a physics vector and returns the comparator function in the way that we expect, get that function that this returns, and then use that as our comparator for our sort. So this solves a few problems. One, we get that information baked into this function, but also we have to comply with the comparator protocol. We have to take exactly 2 physics vectors and return a Boolean. But when we want to do this comparison, we really want 3 physics vectors. We want to take 3 physics vectors. We want also that reference one as well, and then be able to use those 3 to be able to get the distance, to be able to get the relative order, to get our comparator. But we can't do that because merge sort is going to expect a comparator that only takes 2. Merge sort only cares, how do I order these 2 things? And this is how we can get around that. We have a method that takes in the 3rd vector and returns the function in the format that we need for a comparator, and then we can sort based on anything. We have our full capability of sorting however we want. Oops. Any questions on returning functions? This is important for the genetic algorithm. I gave a lot of this code in the handout, but the cost functions, the genetic algorithm needs to take some potential solution of some type and return a double, which is going to be its cost, to figure out how effective that solution is or isn't. And for a lot of those, we need a lot of information more than just the potential solution. For example, for polynomial fitting, which we'll see towards the end of today's lecture, we need a set of points and a potential polynomial and measure how well this polynomial fits to this set of points. That's what we're really after. So how do I get a cost function that just takes a polynomial? Well, we're going to use a method, write a method that takes the list of points and returns a function with those points baked into the function. And that function itself only takes a polynomial. But that function is custom built at runtime to be able to tell how well that polynomial fits that exact set of, that exact list of points. So we can still fit the interface for the genetic algorithm, which just needs to take one solution and figure out the cost of it. All right, no questions on returning functions? Okay. Let's shift gears a little bit and talk about those methods we saw at the end of last lecture. So these, I linked to some documentation. In Scala, they call these collections methods, or collection methods. These are methods that are going to really compress our code and make our code much more descriptive in the way that we write it. And of course, stuff that I'm forcing you to use on these assignments and the homeworks by taking away var. So I'm pushing you to get some practice with these, to get a feel for how this works, and hopefully you'll see the benefits of it. And I think it really changes the way you code a bit when you're just describing what your code does instead of how your code does it, and you're not getting bogged down with the details quite so much. So let's take a look at these. We'll just do kind of rapid fire examples. I'm going to show you a bunch of the useful methods. And then we'll dive into the polynomial code from the genetic algorithm and talk about how that works. How we use these to get that done. All right. Let's just go through these. For each. Admittedly, not too useful. I guess depending on what you're doing. I use it throughout these slides just to print things to the screen. Outside of that, there's not too much use for this. But for each is going to take a data structure, a list in our case, and call some function on every element of that list. The only reason this isn't too useful, especially if you're embracing functional programming to its fullest and not using any state, is you're only using this for the side effects. For each doesn't return anything. You're giving it a function that returns unit, because it's not going to do anything with the return values, even if there are any. So you're only calling this for the side effects. In this case, the side effect is printing values to the screen. So if you want to print values to the screen, or if you have mutable objects and you want to change those objects, then this can be very helpful. But if you're not allowed to use mutability or state or anything, the usefulness of this really cuts down, really cuts back. So for each calls this function on each element of the data structure. Not too crazy yet. Filter. Can we recall a method that is defined outside of the method? Can we recall a class? I'm not quite sure what you mean by that. In the return call. I mean, you can call, we always call methods that are defined outside of that method. I don't really understand the question too much. I'll explain the underscore. How do you subscribe with Twitch Prime? Yeah, you don't. If I go with the partner or affiliate, then you have to watch ads when you turn on lecture. I'm not doing that. No ads. All right, so let's talk about these. Filter. The next one is going to take a function that takes a type of the data structure type, so string in this example, returns a Boolean, and returns a new list containing only the elements for which that function returns true. So we want to filter out these words. I have these very exciting data structure here with just these 4 words, and I want to say I'm going to filter out the words where the length is greater than 3, or filter, so I only have the words that are length greater than 3. And you can see already how this is becoming more descriptive. Words, this is the data I want to work with, and I want to filter based on this filter. So put my words through this filter and give me a new list, and then for that list, for each element in that, print line. This would take us a bit more code if we were doing this, what we call procedurally, which is the way you code in 115. And it wouldn't be, and it would be much so describing how it works, which is what we're supposed to see in 115. How does this stuff work? But now that we're getting to the point where if I gave you a question and asked you to return a new list with elements filtered out of it, like you can write that. You've wrote code like that, tens of times at the very least, maybe hundreds. You've written something following that accumulator pattern, but with some modifications. You can do that. We know you can do that by now. So now we're looking into functional programming and seeing how we can make our code more descriptive and just say, okay, let's filter out based on this Boolean expression, which is a function in this case. The underscore syntax, we saw this last time very briefly. You can use the underscore syntax when as a shorthand to fully defining your function. And I'll use that syntax throughout this lecture. There's one case where I won't, and I'll take a quick pause and talk about the underscore notation a little bit more when we get to that one. But the underscore notation, if the type can be inferred, then you can use this underscore notation to shorthand your function definition. This is the same as saying, defining my parameter list and saying s of type string, and then equal greater than my arrow for the function definition, s.length greater than 3. It'd be the same as typing all that out, but we can use this shorthand if the type can be inferred. If I put an underscore here, Scala's going to know that right here, filter is expecting a function that takes a string and returns a Boolean. This evaluates to a Boolean because I'm using the greater than method. So it's going to infer that the underscore is of type string and that that is meant to be the parameter of that function. We can get away with this as long as the type can be inferred, and in this case if there's just one parameter, but we'll see an example of 2 parameters later. Specifically, you can use this if you only need to use the parameter one time, then you can use this syntax. If you have to use it more than once, you'll get syntax errors, and you have to use your more expanded full definition of the function. All right, let's keep ripping through these. And these are all implications of this idea of first order function. So we have the concept down of what we're doing here. We can take functions as parameters, we can use them as arguments, we can return those functions as return values. Now these, I'm going through them fairly quick. These are all just examples. This is what you can do. These are the implications of being able to do that. Here's a lot of things you can do with that new power, with that new understanding. So map is going to take a function. This is like last Monday's lecture question. It's going to take a function and apply that function to each element of the input data, of the data structure, and return a new data structure with the return values of that function. So here, I have my numbers, 1 through 5, and I'm going to take those numbers and map them using this function, which is going to just square each number. I get all those numbers squared in a new data structure, and I'm just going to print them to the screen. And I get what I would expect if I take these numbers and square each one. I get those in a brand new data structure. And most of this is just setup. Like, this is where all the action happens in not a whole lot of code. Again, you could do this with the accumulator pattern, and you've done things, you might have done this exact thing before, compute the squares and put them all in a data structure, but we can compact that so much more now. Numbers.map, I want to map these numbers with this function into a new data structure. It's done. Map, the method map also takes 2 type parameters. In the last example, both of those parameters were double. But we can actually map into a new data structure of a different type entirely. So if I have my strings from the other example, and I want to map those into a list containing the lengths of each one of those strings, it's not stop me from doing that. I can give map a function as long as the function takes in an argument, or in a parameter of the type of the list that I'm calling this on. The return type can be whatever I want. I can return any type as long as that's matching whatever I'm expecting on the other side. Here I'm just going to take the length of each one of those strings and get a new map, a new list with all of the lengths of each one of those strings. So if you have a data structure and you need to convert that into a new data structure of a completely different type, and you're not allowed to use var, this is pretty much either this or yield, which we'll see next, are 2 of your options. If you need to convert, if you need to just change the values, I have this data, I need to change it into something, I need to apply something to every element and get a new data structure, map is your best friend in that case. Or what we saw earlier, yield. Yield is another syntax for map. Scala will actually take the yield keyword and convert that into a call to the map method. But there's a different syntax and can be helpful in certain cases, depending on your setup. But if I iterate over these numbers and put yield like we saw last time, right after the start of a for loop, where I set up the iteration, and before the body of that loop, I'm going to put that keyword yield, and what this is going to do is take the last expression that's evaluated during that loop for each iteration of the loop, collect all those into a data structure, and return that data structure. So now I'm iterating over these values, and I'm yielding the squared values of each element, and doing the exact same thing that I did with map, but using a little different syntax. So this is more of an option for you. This can, in this example, It was a lot cleaner to use map, but there are some nice places where you might want to use yield, which is, for example, if you don't have a data structure yet. Sometimes it's just a little more convenient to use yield. If I don't have a data structure, I could do in parentheses 1 to 5 dot map. You can use that syntax too. But sometimes, I mean, this one's, I guess, just depending on preference. What you want to do, you can iterate over those and use yield instead. And for my personal preference, I like using yield when I have a function that's more than one line or getting a little bit complex with the logic. I don't like using map and then jamming it all into map. I don't know. That's just my thought. Yield or map, whatever one you want to use, go for it. Any questions at this point? Because I'm just going to keep ripping through these. Any question conceptually about what we're doing? When would we use for each as opposed to for loops? Whenever you feel like it. And that is a serious answer. It does the same thing, but it's different syntax. It's just a different way of typing the same thing. You can use a for loop if you want. You can use for each if you want. But once you get used to the for each, it's just a lot more compact way of expressing the same thing, of being able to accomplish the same thing. So for example, if you want to do for data in data structure, and then the body of a loop, print line data, you can compact that whole thing into data structure dot for each print line. It's just a different way of doing the same thing, but with different syntax, and arguably, I'd argue, cleaner syntax to make our code. I'll regret saying this with the current example on the slide, but making our code more readable. So it's, let me put a different example on the slide. And making our code more readable instead of being bogged down with all the details of what we're doing. If I wrote this out without using map, I would create a new empty list of ints, iterate over words, and append to that new list of ints that I created for each iteration after computing the length. There'd be a lot more stuff going on in the method that doesn't necessarily need to be there if we use for each. Yield. Yeah. Question in chat. Still not quite sure what yield does. So yield is we're going to iterate over this data just like we would a normal for loop, except instead of just executing the code in the body of the for loop, we're still going to execute that code, but then the last expression that's evaluated during each iteration of that loop is going to be collected into a data structure. So we can think of, using yield, we can think of the body of the for loop somewhat like a function or a method body, where the last expression that's evaluated is going to be returned. So we're thinking of each time the body of this loop executes, the last expression is going to be returned in a sense. It's going to be returned, and all those return values are going to be added into a brand new data structure. They're going to be collected into that data structure, and that's what's returned from this entire thing. So this entire for yield, all of this evaluates down to one data structure with all of those values that each iteration of the loop resolved to. When we use yield, it's going to try to match the type of the data structure that we iterated over. Of course, the type contained in the data structure, int in this case, that can change just like map. We can change the types, whatever this resolves to, that's going to be the type of the type parameter of the returned data structure. but the data structure type itself is going to try to match whatever we iterated over. So for example, in this example, numbers was a list. So Scala, when we say yield, it's going to return a list. It's going to match that data structure. It's going to this result to a double, so it's going to return a list of doubles. Sometimes that can't really be done, and Scala is just going to kind of make up whatever it wants to as its default option. It's actually a vector in this case. 1 to 5 is a range, and I can't have a range of doubles. Range is a specific data structure that we can't have that range of doubles. So what Scala is going to do when it sees yield, it's going to just use whatever data structure it wants. I mean, it's defined what it's going to return, but it's often not going to be a list, or maybe never going to be a list. So if we have that, this whole statement here, for yield, the body of the loop, that entire thing resolves to that data structure that was created using yield. So I'm going to put parentheses around this entire thing. So inside those parentheses is that data structure that was created using for yield. I'm going to convert that to a list. Now I can have a list of doubles, and I don't have to worry what data structure Scala decided to use. I don't have to care that it returned a vector. I just know I want to work with lists because the lecture question says return a list. So hit it with that to list. You don't have to worry what data structure it actually ended up giving us. Yeah, it's most of this. Yeah, this is all. It's kind of one little bit of sad thing with this lecture. We're not learning anything. You're not learning how to do anything new. You can do everything that we're seeing in these slides, except returning a function, I suppose. But even then, we could do custom sorting with objects and classes. We could do that. But these are different ways of accomplishing the same things. That can clean up your code and also optimize your runtime, optimize your code quite a bit. There's, when we have this syntax, for example, the for yield syntax, it doesn't matter, I mean it does, but it doesn't. But whatever we have inside here, Scala knows that anything we do inside the body of that loop, we're not concerned about unless it helps us build this data structure. So anything we have in the body of this loop, it's just going to say, okay, I get what you want me to do, and that's where our descriptive code really comes in handy too. Another way that this comes in handy. Scala can say, I get what you want me to do. You want me to iterate over this data and create a new data structure by evaluating the body of this loop. And since it knows we don't care about the internal details of what we coded, the compiler can optimize that for us. So for example, when I keep mentioning whenever you work with a list, you're creating a brand new copy of that list. Or whenever you call .apply, you have a very expensive operation. You have to hop all over memory to be able to get that done. Well, if we have these setups, we can avoid those types of issues by saying, hey, compiler, this is what I want to do. And then Scala can take over from there and say, okay, I'm going to do that most efficient thing that I know how to do, that teams of engineers have spent decades coding and optimizing. Let me do that instead of whatever you would have coded if you weren't using these, which is going to be something really inefficient, like my selection sort algorithm, where I'm doing really sloppy things with lists. If we avoid telling our code, this is how we want to accomplish something, and just say this is what we want to accomplish, where we're really giving the compiler more opportunities to optimize our code and get much significantly faster runtimes out of our programs. So a few reasons. One, compact our code, and it's just, Sometimes just cooler to have your code more compact and more descriptive, but also there's an efficiency, a more practical reason that the compiler can have more opportunities to help you out and more efficient code as well. All right, let's see a couple more of these. Reduce is a very handy one. With reduce, we can take a data structure, give it a function that takes two values of the type of the data structure and returns a value of that same type, and it will apply that function to every element of the data structure and compress this whole data structure using that function into a single value. So if I want to compute the sum of the squares of a data structure, for example, I'm going to create a function that takes two doubles and adds the first parameter to the square of the second parameter, and then call reduce on that function. Reduce is going to call that function on each element of the data structure, starting with the first two. Let me back up. Starting with the first one, and the first argument of that reduce call is going to be the accumulator variable. So this is a way of doing the accumulator pattern in just one quick line, dot reduce, give it a function, and it'll accumulate based on that function. The first argument is going to be the accumulator variable. The second argument is parameter is going to be the current element that we're looking at. The accumulator variable is going to be initialized to whatever 0 is effectively for the data type that you have. So in this case, doubles, it's going to be 0. Strings, expect empty string. Integers, 0. So the first time sum squares is called, I'm going to have 0 as my parameter A, and then B is going to be the first element of my list, which is going to be 1. 1 squared, I'm going to get 1 out of that, and then that's going to be my new accumulator variable. So now next time sum squares is called, A is 1, and B is the next element in my data structure 2. I'm going to square 2, add that to 1, and get 5. The next time sum squares is called, A is going to be 5. B is going to be the next element in my data structure 3. I'm going to square 3, add that to 5, and get 14. Then A is 14, B is 4, and keep going throughout the entire data structure like that. So if you have this kind of a setup where you can start at 0 and keep calling this function on every element and keep accumulating the values, reduce is going to give you this nice syntax. And here's where I split this into the more traditional, we just started it last week, but more traditional way of writing our functions, where I have a function, 2 doubles to a double, 2 doubles to a double in the body of the function. We have 2 parameters now for the function, but we can actually still use the underscore syntax. We can rewrite that function with the underscore syntax, cut down a lot of that typing. And when we have 2 parameters, the order in which the underscores appear is going to determine the order of the parameters. So in this case, the first underscore that's found, that's going to be the first parameter or the first argument, and the second underscore that's found, that's going to be the second parameter or second argument in this function. And now we can see if we do need to use one of the input parameters more than once, we can't get away with that with the underscore syntax, because how do you specify, if I had 3 underscores here, how do I say, no, 2 of those underscores are the first parameter twice, and the second one, or the third one, that's the second parameter once. We wouldn't have a way of expressing that. So this is the way Scala chose to do it. Just the order in which the underscores appear is going to be the order of the parameter list. So we have to make sure that our accumulator variable is the first underscore, and our current element that we're looking at is the second underscore. If we get that order mixed up, we're going to have bad results. Fold is very similar to reduce. But there are two cases where we would use fold instead of reduce. One, if we want to initialize our accumulator variable to something other than 0. So if I want to compute factorial and I use reduce, and reduce is going to initialize my accumulator at 0, well, guess what? I'm always getting 0. That's not helpful to me. So if you need to set some initial variable, fold is actually a method that's going to take the initial accumulator variable and return a function with that initialization baked into it. And then after that, it's almost the same as reduce after that. So I'm actually calling a method which is returning a function, and then I'm calling that function. So if you haven't had your fill of functions and chaining things together, gets crazier. It's a whole new way of thinking and a way of approaching our coding. But we just called a method that returned a function and then called that function all in one line. That's why we have two sets of parentheses here. And then I'm just multiplying. So take the first argument, the accumulator, and multiply it by the current element that I'm looking at, and I'll get my factorial out of that. Oh, I do have it. I thought I did a second example. Fold, you would also use this if you're changing the data type. So reduce has to take two elements of the same type, of the data structure type, then return that same type. You would use fold. You would also use fold if you either want to initialize this accumulator to something else, or if you want to change the type. If I want to take my list of strings and sum up the length of all the strings in that data structure, something where I'm taking data of one type and I'm accumulating into another type. You would also use fold for that. Reduce isn't going to let you get away with that. It's not going to let you have two different types. But fold, your accumulator has to be the accumulator type. The second argument, that's going to be the type of your list. And then the return type has to be your accumulator type again. As long as you're fitting that protocol, then fold is going to go through your data structure and accumulate all that. One quick note on these. All of these work through your data structure from left to right in your data structure. If you want to work through your data backwards, you would append right to the end of each one of these. There's a fold right, a map, a reduce right, to be able to work backwards through your data structure. So if that's important to you, if you need to go backwards through the data structure, those exist by default. And you'll see left and right in some of the handout code that I gave. But they'll all default to left. They'll go from left to right or from the beginning of your list to the end. And very quickly, let's see this quick example of this. So some a little more involved, not too crazy. But the polynomial code, this is in the handout for the genetic algorithm. I also put it in the wrong folder, week 7 it should be in. But I also put it in the examples repo. So a polynomial is represented, we're representing these by a list of coefficients, starting with the highest order coefficient. Then if a coefficient is missing, we would have to put a 0. We put a 0 there. So we have all the coefficients for a polynomial. And then to evaluate, I'm going to call reduce at my accumulator and my coefficient. I spelled this out just because I wanted variable names. So I used the more expanded syntax just so I didn't get too lost in all the syntax. But my accumulator and my coefficient, I'm going to take my accumulator, multiply it by x, and add it to the coefficient. So the first time I get this, I'm going to take my leading coefficient and just add that to 0. My accumulator is 0 times x. I just get my leading coefficient, 1.5 in this example. The next iteration, I'm going to take 1.5, multiply it by x. So I have 1.5 times x, and then plus a negative 2.2. Then the next iteration, I'm considering 5. I'm going to take 1.5 times x minus 2.2, multiply that by x, and then add 5 to the end of that to get my total evaluation for that value of x. So I can evaluate a polynomial with reduce by tracking how that's going to go through the reduce method and how that's going to be called. And then for our cost function, given a set of points, giving a list of points, I want to figure out how well a given polynomial fits those points. So I take the list, and first I'm going to return this cost function that takes a polynomial and returns its cost with those points baked in. So I'm setting up my function syntax. I'm going to use fold, which I could just use fold here. So I could just use reduce there, couldn't I? So I'm going to fold this in and take, no, I have to use fold because I have different types. I'm going to take the total accumulated distance, take the current point I'm looking at, compute the distance, the square of the distance between this point and the evaluation of the polynomial looking only in the y direction. And once this returns, I'm going to divide that by the total length to be able to normalize based on the number of points. So if I have more points, I don't want that to penalize my cost. So I can use that fold to be able to take in a list of points and return the total squared distance of the evaluation of this polynomial and the distance between those points. How far are these points away from the polynomial? And with that, see everyone Wednesday.